You know, it's hard to tell that light is in waves. It wasn't until the early 1800s when a scientist named Thomas Young discovered that light produces interference when he shone a beam of light through two openings. So if you have a situation like this where light is hitting a solid substance, but there are openings in that solid substance, kind of like here, this is kind of an extension of it. The solid substance with through here, you have the light coming out, and it produced interference from the light coming from the bottom, from the light coming from the top, and it produced interference. And it actually produced a striped pattern, a pattern that looked like stripes. And after thinking about why shining a light through here made a striped pattern, he concluded that since it made interference, it was made of waves. Now, it does seem that light has other characteristics of waves. I mean, if you hold up a mirror and you shine light on it, it reflects. Light seems to go around things or go through things, so it diffracts. And it also refracts. I mean, look at the experiment with the pencil inside a cup of water. I mean, that's the light that is refracting. So light seems to do things that waves do. Yet, light does seem to have qualities that waves don't have. Now, you kind of get the impression as you study this that scientists really don't have a firm grasp upon what light really is. I'll give you an example. Light, if you were to have a bright, here it is, if you were to have a bright or dim blue light strike a metal plate, electrons fly off the metal surface. Somebody discovered that at some point. But if you have waves, waves are not substances. Waves don't have atoms. So why does light produce electrons? Also, if you shone a bright red light onto the same metal surface, no electrons fly off. And bright red light should have more energy and higher amplitude than dim blue light. So why do you have electrons going out from this dim blue light? So it kind of begs the question, are light waves or is light particles? And you know, scientists are really kind of struggle with that a little bit. Some think it's true that it's particles, and we actually have a term for that called a photon. I don't know if I have put it on here. I don't guess I have put it on here, but photon is P-H-O-T-O-N. So if light is not in waves, scientists have already said that it would be in photons. Now, a photon is considered a particle, but it's considered a particle without any mass. If a light shines on your hand, that does not add to the weight of your hand. It does not have any mass. But scientists who are of this train of thought think that photons are particles. And like I said, you kind of get the impression that scientists are a little uncertain about this whole light thing. They say that these photons are just little beams of energy located in a specific place. So, what is true? Is light a wave or is light a particle? Well, this is the scientific community's version of shrugging their shoulders. Currently, most scientists accept both the wave idea, or the wave model, and the particle model. And scientists, in an unscientifically fashion, use one model depending on the situation, and another model depending on another situation. Either way, whether light is a wave or whether it is a particle, It does contain energy. That much seems pretty certain. So let's go to study a little bit more about this light energy. The amount of energy depends upon the frequency of the wave. Now you may remember that frequency has to do with how often the sine curve goes from crest to crest. It depends on the wavelength divided by the time. So the closer the waves are together, the more frequency you would have. And you can see the term frequency up here. The higher the frequency, the longer up here it goes. Now this is pretty high here, 10 to the 24th power. That's a lot of zeros after the 1 here. And even down here, these radio waves are a lot closer to a manageable type number. But notice what we see. We only see right here about 10 to the 15th power. We actually have waves here. In fact, you've heard of them: X-rays, microwaves, UV waves, radio waves. We just don't see them. And when's the last time you looked in the microwave and saw the waves cooking? You just don't see them. We only see this little stretch right here. This is called the visible spectrum. Along the visible spectrum, each color represents a different frequency. So if the frequency is faster or is higher, then it's toward this end of the scale, and it's toward lower, it's toward this end of the scale. Now they have it kind of flip-flop. I think here is where they have it flip-flopped at, because the blue, I believe, would be the lower wavelength and the red would be the higher wavelength. But still, just a little bit apart here that we can see, and the red has the higher wavelength than the blue. The speed of light is much faster than the speed of sound. We have a number down here, 186,000 miles per second. You know how whenever we were talking about speed of sound and we said something like, if somebody at the other end of the field shoots a gun, you can see the explosion coming out of the gun quicker than you hear the sound. The sound might be kind of a delay. So the speed of light got to that person's eyes, the light got to that person's eyes before the sound got to that person's ears. Now think about how big 186,000 miles is. The circumference of the earth is not even close to 186,000 miles. So you could go, light could travel completely around the earth in less than a second. The moon is about 200 something thousand miles to earth. So it takes 2 seconds or less from light to reflect from the moon to the earth. 2 seconds, 1, 2, and that's how long it takes. Nothing we have found in the universe, we have found nothing faster than the speed of light. Notice something else. It travels through transparent mediums. It travels through air, it travels through glass, it travels through water. You may remember it doesn't even need a medium in the first place to travel through it. That's another reason that some scientists think that it might not be in waves. But anyway, the speed of light is different for different mediums. Kind of like the speed of sound. You know, the speed of sound was different whether you're underwater and over water. Speed of light is a little bit different also, but the constant speed of light is 186,000 miles per second. Now you may have noticed that a 100-watt light bulb is brighter than a 60-watt light bulb. The quantity that measures the amount of light shining on a surface is something called intensity. Hey, we use that term when we're talking about sound waves. Yes, this term is used in sound waves and in light waves. So a 100-watt bulb would have brighter intensity than a 60-watt bulb, just like a louder sound would have more intensity than a softer sound. The intensity, as far as light concerned, is the number of photons that pass through a certain area of space. The intensity decreases as it spreads out. So if I'm standing here next to this, say, 100-watt light bulb, it has a lot of intensity. But if I'm standing 1 mile away from that light bulb, it doesn't look like it has a whole lot of intensity. It is relative to your distance to the light. Intensity decreases the farther away you get from the source of light. Even the sun, if you were out at Pluto, what used to be known as planet, the intensity of the sun is not as heavy out there, or not as much out there. A bright light bulb is only bright near the bulb itself. Well, I hope you learned a little bit about light. I know we have another video continuing light that will come up sometime after this.